And I'm going to start out by saying, in my presentation for you today, I'm going to tell you a little bit about how I ended up here at PAX talking about quantum mechanics. And then I'm going to teach you everything you need to know about quantum mechanics in about 25 minutes. And then after that, I'm going to tie that into some alternate reality and how that actually leads to smaller areas. And first of all, just thank you all for coming. You obviously are the ones in PAX that are most interested in the scientific subjects. So I'm not a quantum scientist, I am a software engineer. I came to the world of quantum computing. Just as a special interest, I would look into quantum computing and read the stories and the articles, just to see if I could figure out what was going on there, what sort of things we're going to be able to do with these quantum computers in the future, perhaps what I could do with them today. And I quickly realized that a lot of the articles didn't make any sense to me, I didn't understand it, and I needed to actually understand quantum mechanics much better than I did to really understand quantum computing. So I embarked on a journey. It was a months-long journey, I would argue 10 years-long journey, where I dug into the issues of quantum mechanics so that I could really understand quantum computing. And I pretty much became obsessed, because it just completely blew my mind what I found out about the basic understanding of quantum mechanics. And when I say I became obsessed, I wanted to blow other people's minds. And so I would try to explain anybody who would listen. I would explain quantum mechanics, and I honed down my ability to get across that information to people. It actually was kind of a joke in my house, because my high school-aged daughter, I found out she was telling her friends that if they came over to our house, there was a toll that needed to be paid. And that toll was that I was going to sit them down and teach them quantum mechanics in about 20 minutes, right? So, and they still are doing that today. I have other high school age kids now. But what I did then, after I condensed the quantum mechanics part down, I then tacked onto it some quantum computing elements, created about an hour-long presentation, presented it in a couple of different places. And so that's how I came to speak on quantum mechanics itself. Now, how I ended up here at PAX. In January, I was at PAX South. I was just talking to somebody I just met, and they were referring to a game. I don't remember which game it was. I think it was Chrono Cross, but they were referring to the to the alternate reality of the narrative of the game. And they were talking about that, and immediately my mind went to all these other games that were employing these alternate realities. And I'm like, this is a common thing. And then I realized, because of my exploration in quantum mechanics, I realized there's actually a base root here. I mean, I know that there's a base root here of quantum mechanics leading to possible alternate realities. I wonder how many other people know that. And then I asked, I wonder if a PAX audience would be interested in that subject. And so I modified the presentation. I employed some help from some friends to help me hone it down. And I submitted it, and it was accepted at PAX. So that's how I ended up here. And when I started to dig into these games that actually have all these alternate realities, I realized pretty quickly it's not just games that have that, it's also television shows, movies, and yes, even webcomics, right? It seems like this is such rich fodder for storytelling. There's a tropes page on it that talks about it. And it's so prevalent that there's Wikipedia pages that catalog the use of alternate realities in all of our fiction, in all our narratives. So obviously this excites the imagination and allows us to tell stories that we otherwise wouldn't be telling. And so yeah, I thought that was actually really interesting when I was looking into that. Now when I tell people I'm going to teach them everything they need to know about quantum mechanics in 20 minutes or less, most people say they don't believe it. They tell me, no, you can't do that. That's crazy. What are you talking about? In fact, when I said it earlier, I could see a lot of smiles and like, yeah, sure, you're going to be able to do that. And I think as I've gone through this exercise of teaching a lot of people this, I realized that there's two main reasons why people think it's inaccessible to them, right? And the first reason is illustrated by this picture. It's because people think, no, quantum mechanics, that's what the smartest people in the world came up with, and that's what the smartest people in the world are working on. And they're also using some very involved mathematics to make it happen. And the reality is, that's right. Absolutely, the smartest people in the world are working on it, and there's a lot of involved mathematics. But I'm being very specific when I say I'm going to teach you everything you need to know about quantum mechanics in 20 minutes or less. You don't need to know the math, right, you're still going to be able to understand it. There's not a single equation in my presentation at all. Okay. The second reason why I think that people think it's not accessible to them is because if they started to look into quantum mechanics and they started to really try to understand what was happening there, they quickly got to a spot to where they realized they didn't have any idea what was going on. They were very confused by what they were studying. And they think that it was a limitation on them. They were thinking that they weren't able to understand it because they just weren't enough to make it happen. And the reality is, it's actually a limitation on the material. The material is just confusing, and it exposes some strangeness in our universe. It's actually something that everybody gets confused about, okay? And so my presentation here today, what I'm hoping to be able to do is to get us to the spot to where you're confused about the stuff you're supposed to be confused about, but you understand all the other stuff, right? That's where I hope to get. And when I say that everybody comes to that spot where they say we don't really understand, let me give you some examples here. This is Niels Bohr. He is the main pioneer of quantum mechanics. And here's what he had to say about it. When I say he's the main pioneer, he's the guy who pretty much came up with the interpretation, and I'll define that later and we'll understand it. But he basically says that you need to have a profound shocking in order to really understand it. This is Max Planck. He's another pioneer of quantum mechanics. Here's what he had to say about it. He said that it may be a little unclear what he's saying here, and I'm actually going to come back to this quote later, and I will make it very clear to you. But you have to admit that when he's talking about how science can't really solve the mystery of nature because we're a part of it, you may not understand what that is, what that means right now, but it is pretty bizarre. I have to admit it's bizarre for a scientist to say that science can't solve the ultimate mystery of nature, because that's what scientist was for. It was created to explore nature. And for him to be so fatalistic, you have to admit it's a little bizarre. But I will come back to that later and I will explain to you exactly what he's talking about, and you may actually agree with him at that point. This is Werner Heisenberg. He's well known in physics circles for the Heisenberg uncertainty principle, another pioneer of quantum mechanics. Here's what he had to say about it. He says that it's stranger than you can even think. And while I say that he was well known for the Heisenberg uncertainty principle, he's probably more well known today as the alter ego of one Walter White. This guy you guys all know, Albert Einstein, he's pretty much the grandfather of quantum mechanics, and I will explain that further, how he became recognized as that. And it may be a little unclear here about what he's talking about. He's talking about God not playing dice with the universe, and I will explain that later as well. But I want to give you a little bit of background here. He was the grandfather of quantum mechanics. He was the first one to expose the quantum and to put it in a place that really kind of blew our minds and exposed some strangeness in the universe. And I will come back to that later. But he then went and worked on relativity. He didn't finish working on this. He turned it over to other physicists like Niels Bohr, and they carried it forward and developed a whole mechanics, and it started to be a very successful theory and revealed some very interesting things about the world around us. But Einstein actually took a step back, because while it was a very successful theory, the interpretation of the strangeness he was not comfortable with. And this is one of the elements, specifically saying that things are not deterministic. At the fundamental level, things are not deterministic in our universe, that they rely on a randomness. And that's why he was a scientist who knew the value of a good soundbite. And so he would say, God does not play dice with the universe. Now, his rival was Niels Bohr, and this was a rivalry that lasted the rest of their lives. Einstein would constantly try to come up with thought experiment after thought experiment to disprove Bohr's interpretation. And it's actually called the Copenhagen interpretation because that's where Bohr was from. And that's the main interpretation of quantum mechanics, and I'll explain that in a bit. But he kept trying to disprove this Copenhagen interpretation. He was never able to. Niels Bohr was able to fight back these thought experiments and to prove that there was something missing there. That's not to say it was proven right. It just wasn't disproven. The Copenhagen interpretation is just not disproven. And so this rivalry went on, and every time Einstein would say, God does not play dice with the universe, Niels Bohr would reply with, stop telling God what to do. This guy, his name is Richard Feynman. He is a Nobel Prize winning physicist. He won his Nobel Prize in quantum electrodynamics, so he's a quantum scientist. And here's what he's saying about quantum mechanics. He says nobody understands it, even the Nobel Prize winning physicist. And lastly, there's this guy. His name is David A.B. Miller. He's a professor out of Stanford. He teaches an online course called Quantum Mechanics for Scientists and Engineers. It's freely available. We live in an amazing time where we can literally learn anything. And here's, in his introductory video to the online course, here's what he has to say about it. About what I was saying earlier, that you need to allow yourself room to have that psychological struggle with this material. Be okay with the fact that there's some of it that doesn't make sense, and then just move forward so you can actually learn the rest of it, because that's just part of the journey. Now, I'm going to teach you the quantum mechanics in about 25 minutes, right? I usually say 20 minutes or less, but I added some stuff on the end to really drive some points home. And how I'm going to do that is I'm going to go through a history of a scientific question throughout the ages. And that one question is, what is light? Over here on the right, you have a light bulb that has waves emanating from it, and it's representation of light as a wave. And over on the left, you have a light bulb with particles coming out of it. It's representation as light as a particle. Now, we knew early on that there was some fundamental properties, there were some fundamental natures of things that are waves. Waves is just a thing by itself. For example, sound is a wave. And what that does is it actually creates a vibration in the air, and it has all the properties of a wave. It has wavelengths, it has frequencies, periods, all that kind of stuff. And depending on those properties, it'll create a different sound inside our ear. That's that energy transfer of sound. So we knew that there are fundamentally some things in nature that are sound, or that are waves. But then also, all this stuff is made up of smaller and smaller stuff, right? And so the question was, is light like sound? Is it a wave? Or is it like everything else and it's just very, very, very small particles? In the late 17th century, this guy came along. His name is Christian Huygens. And Huygens was a scientist. He did a lot of experimentation on light, and he came to the conclusion that light was a wave. And I won't go through all the experiments, we don't have time, but I'm just going to tell you one reason why he thought light was a wave. There is a property of waves called diffraction. And you don't need to know that name. You actually intuitively probably already understand it, but let me explain it to you. All diffraction is it means that as a wave is traveling, when it hits a wall, and that wall has a hole in it, the wave doesn't continue in a straight line the width of the hole, right? It doesn't just continue that way. And of course, we intuitively know that. We think that's crazy that you would think that, but think like a scientist, think about all possibilities. Because what happens there is the wave actually bends around the corners and spreads out like you see in this picture. You can see that wave is hitting the wall and then it's spreading out behind it. You can see the wave expanding to fill up the entire space. That's what diffraction is. And Huygens said similarly, if you had a dark room and you had light on this side and you had a wall and then you punched a hole in the wall, the pattern that it would create on the ground looks like it's a spreading cone-like pattern, like in this picture, right? And so he looked at that and said, that looks like diffraction. I'm going to say that's diffraction, and so I'm going to say that light is a wave. But Huygens actually had a contemporary by the name of Sir Isaac Newton. And Newton also did a lot of experiments with light. He literally wrote the book on light, and he came to a different conclusion. He said that light is actually a particle. And I won't go through all the experiments there. Let me just show you one idea of why he thought so. This here is an example of something called refraction. And again, you don't need to know the name, but you already probably intuitively understand it. And what that means, let me explain it to you. If you look at the bottom of that straw and you follow that straw up all the way to the top of the water, it actually looks like that straw is now continuing over to the left as it goes up. Now, we all have experience with water distorting our vision, and so we already know that it's really just one straw in there, and it's just the way it looks. It's not actually mangling of the straw by the water. We pull it out, it's going to be the same straw. All it is just a visual effect that's hitting our eye. And Newton did a lot of work with this kind of thing, this refraction, and he realized that there were some very sharp angles. That what was happening is the photons, as they were hitting the water, were being ricocheted or bent at a specific angle. And so as we see it, because it's being bent by the water, it's just hitting our eye, and so it looks like it's in a different place, okay? And so that's called refraction, and he said that kind of sharp angling, that looks like particle. It's like a bullet being ricocheted off of something. He said waves would actually spread out more, and it would be more of a smooth type of effect in our perception. And because of who he was, so because of that angling, that sharp angling, he just basically said it's particle. And he pretty much won the day because of who he was. He was Sir Isaac Newton. And he had some good arguments too, but so did Huygens. But the truth is, if Sir Isaac Newton tells you something about the nature of the universe, it'd probably be pretty wise to listen to him, right? Because of what he did before that. And so everybody did. They said, Newton says it's a particle. He even came up with this pre-atomic theory of particles called corpuscles. And he said that the corpuscles, that light is made up of these very small corpuscles. And people believed that for 100 years, until this guy came along. His name is Thomas Young. And Young basically was a scientist, which means he's not just going to take somebody else's word for it. He looked at Huygens' arguments, he looked at Newton's arguments, and he said they all seem to be pretty legit. So he said, we actually know enough about the properties of waves that we should be able to come up with an experiment to prove once and for all whether or not light is a wave, rather than just take one person's voice over it or not. And in particular, some of the properties he was talking about is how waves interfere with each other when they're close enough. And you can't see it in this image, but on the other side of that guy's head, there's another green ball over there. And he's bouncing those balls on the water very close to each other, and those waves are spreading out, and they are interfering with each other. And very specifically, there are places on that water where the peak of one wave and the trough of another wave are coming together to basically cancel the wave out, that interference. It's called destructive interference. And you can see that happening here in the green lines, right? There's a smooth spots on the water where the wave doesn't exist because the peak of one and the trough of the other are canceling each other out. And Young knew that about waves and knew that was a property. He actually drew this diagram, and he basically said, we can see this same effect happening in light if indeed it is wave. He said all we need to do is create a light source at both A and B. Those lights will spread out and create the interference. And while you can't see the light interference as it's traveling through the medium in the air, because we can't see that like you can inside the water, he said you don't need to see it as it's traveling through the medium. You just need to see how it resolves against the screen, because that interference will be carried out completely. And at C, D, E, and F, you'd see that destructive interference by seeing just dark lines there. And then in between them, you would see bright lines. That was his reasoning. And so he said, he drew the diagram, then said, let's do the experiment. Very simple concept. And he created a box, had a single light source, and this is the name of this very famous experiment. It's called Young's double slit experiment. And so he had a single light source, and then he had a wall with two slits in it. And the idea being that light source would light up both those slits, and then the diffraction would happen at both those slits, interfere with each other, and then you just look at the back wall and see what pattern it is. If it's a striped pattern, then it's a wave. If there were particles, then you would just see a blotch of light behind one of the slits and a blotch of light behind the other slits. So he built the box, turned the light on, and looked at the back wall, and this is what he saw. So he decided, definitively proved that light is absolutely a wave. And he overturned Newton. It's not something that happens that often, right? And so for 100 years, everybody said Young proved it. There were other experiments that also proved it that were pretty ingenious. But he said, this is the iconic one. He said, light's a wave, and so therefore it is. And for 100 years, people believed that. As you imagine, it's not the end of the story, because 100 years later, this guy came along. Einstein, in 1905, wrote 5 papers that all were amazing in and of their own right. Everybody knows him for relativity, mainly. Everybody probably secondly knows him for E equals mc squared. That was another paper. But not as many people know him for the paper that he did about the particle nature of light. Okay? And what's interesting about that is Einstein did not see his work on relativity as being as revolutionary as the rest of us did. He thought it was just a natural progression of what people had done before. He did think, though, that this particle nature of light paper was revolutionary. And the Nobel Committee agreed with him because it was this paper that he won his Nobel Prize for, not relativity. And what he was doing there is what scientists always do. They try to explain the unexplained. And there was a phenomenon that happened with the wave theory of light. There was a phenomenon that happened with light that the wave theory wouldn't explain. It was just unexplained. And that's called the photoelectric effect, okay? And let me describe that effect for you here. On the bottom here, that rectangle is just a piece of metal, okay? Inside that piece of metal is a circle with minuses. All those circles and minuses, those are electrons. And what happens in the photoelectric effect is if you hit that metal with a high frequency of light, then electrons will be released off the metal. But if you hit it with a low frequency of light, electrons will never be released. And what was confusing about that is that it didn't matter the intensity of the light. If you had a very small amount of high frequency light, it would still release the electrons. But if you flooded that thing with as much low frequency light as you possibly could, those electrons would never be released. And that didn't make sense with the wave nature because waves are a continuous energy transfer, right? So it didn't make, if indeed this was an energy transfer that was causing this release, then a high intensity, low frequency transfer should have also released those electrons. And nobody understood why. There was no good explanation for it. And so until Einstein came along. And he looked at it and he said, you know what, guys, it actually looks like what's happening here is that the high frequencies of light, or that light itself, is actually coming in quantized packets of energy. That term quantized, that's the quantum. So it's a specific number attached to the higher frequency of light has bigger and higher number of energy on them. The lower frequency of light just has smaller packets of energy. And he said, so what happens is in that higher packets of energy, they're big enough, it's enough energy on these quantized packets that when it hits the metal, it's like billiard balls hitting another billiard ball, and it would release the electrons. Whereas the lower frequency of light, it's such a small amount of energy, packetized energy, that it would be like trying to throw a feather at a bowling ball and getting it to move, and it never would be able to do that. And so these quantized packets of energy were later renamed the photon, and thus was born the particle nature of light. He said it looks like it's a particle interaction. Now, Einstein was not unaware of Young's double-slit experiment. He knew full well that light was a wave. You know, definitively proven, absolutely. But he also wasn't the kind of guy to let current knowledge stop him from exploring the universe the way it really is. And so he then said, it's particle. Yeah, it's light, but it's also particle. And thus was born the wave-particle duality. In some cases, light behaves like a wave. In other cases, light behaves like a particle. Now, that may have solved the photoelectric effect problem, but obviously that creates other questions. Because this is the first time that we've ever seen a natural phenomenon that was both wave and particle. We didn't really know what it means and didn't understand it. And even today, we don't really know what it means or understand it. And so that's just more opportunity to do more experimentation on it. So we can find out what is this strange wave-particle duality. And what you see here, this is a visualization of the double-slit experiment being done with photons. So the green box is a photon emitter, it's sending them out, and then on the back screen you can see it resolving itself in this wave pattern. Now you can imagine, as you look at this, it's easy to imagine the wave traveling through both of those holes, because the wave would spread out, it would create diffraction behind both of those holes, and then it would just result on the back wall. But what you can't imagine, or what doesn't make any sense, well, you would also imagine that if there's a particle there, the particle would have to go through one of those two holes. It couldn't go through both of them, right? Because that's our nature. Particles happen to be in one place. They don't happen to be in both places. And so they thought that we could look at it and see if light is both wave and particle, maybe if we could create a device, an instrument that would measure which of the holes the particle goes through, and then we can see where it lands in the wave pattern on the back, then maybe we can get a better understanding. Like if we isolated all the particles on the left and say all the ones on the left end up here and here, maybe we'd see a pattern and learn something else about this wave-particle duality. And so they did that. They built a device to observe which of the slits that the particle goes through. They turned it on and it was telling us exactly where the particles were going through. But then something very strange happened, something that was unexpected and is still unexplained today. Because the wave pattern disappeared and a particle pattern appeared. Okay. They took the measuring device away and the wave pattern reappeared. And they looked at this in many different ways. They looked at this, at first they thought maybe the instruments were causing some sort of impact there, or they thought that just the ability to be able to see something, to create an environment to do that, it would actually cause some sort of particle interaction there. They ended up ruling all of those out. And ultimately what it came down to, and this is what Bohr's interpretation is, or the Copenhagen interpretation, ultimately he came to the conclusion that this image is wrong. Because this image is showing the particle of light traveling through space. Okay, and then it resolves on the back. And he said in reality, the particle doesn't actually exist there. That as it's traveling, it is a wave of probability. The particle could be anywhere in that probabilistic place. So it's this wave of probability that then becomes a particle once observed. That once you observe it, it collapses from this wave of probability down to a photon of certainty. An observation consists of this measuring device as it's looking to see which of the holes it goes through, or even when it hits the back wall, that's considered to be an observation as well. And that was that wave of probability. That's what Einstein had problems with when he said God does not play dice. And that's what Bohr is saying, no, that's how it is. Einstein wanted the world to be deterministic, but basically Bohr is saying it's not deterministic. Now Einstein eventually came to terms with that. He was okay because, like I say, it's a very successful theory. Quantum mechanics has explained so much in the world that Einstein eventually came to terms with that. What he never came to terms with, and what he fought with Bohr the rest of his life, was the idea of an observer-dependent reality. That reality exists just as a wave of probability until we observe it, and then it collapses to some sort of certainty. He didn't like that, very uncomfortable. One of his quotes was, he just likes to believe that the moon is there whether we look at it or not. Right? So he became very uncomfortable with that. And they fought for a long time, the rest of his life. Now, this is the part that I normally don't explain to people, but I'm going to actually explain it to y'all because I'm really trying to illustrate here and stress about the strangeness of this, and how as we keep digging into it deeper and deeper, it seems to be just becoming more and more strange, right? And the reason I say that, and the reason Einstein had a problem with observer-dependent reality, because you can see that now we have to start asking questions that aren't science questions, but are more philosophy or metaphysical. Right? The first question would be, what is an observation? What does that mean? And they debated that and talked about it over and over again. It's still being debated to some extent today. Like, what is an observation? One of the initial things that they asked about was, does it need to be a conscious observer to cause it to collapse? And they quickly came to a conclusion that it didn't need to be a conscious observer. And I want to explain to you why and show you how that is. Let's say that instead of the eyeballs there, the eyeballs are conveying some concept of consciousness behind it, right? Let's say instead of the eyeballs, we actually have an instrument, an unconscious instrument, right? And let's set that instrument up to record which of the slits that the photon is going through. And then we turn on the photon emitter and have it emit a photon like every half second. And then we take our consciousness away from the experiment and we go have lunch. And then watch a movie and go golfing, play some video games, waste a couple of hours. And then when we come back, there's no consciousness here at the time. When we come back and take a look at it, we then see that there's a particle pattern, which means that unconscious instrument was able to cause the collapse to occur. Okay? And so that seems to settle the question that whether or not it can be conscious. It doesn't need to be because this was able to do it. Now that assumes the reason that we think that's fine is because we're assuming that our later observation, us coming back later and observing the results, would not affect the previous measurement, right? Because that would be a cause coming after the effect. So we assume, that's a logical thing to assume, we think that's great. And when I say it's a logical thing to assume, now let me show you this experiment. This is, was done in 1999 for the first time. It is called the Delayed Choice Quantum Eraser. And it was done out of University of Maryland, a team led by Yoon-Hoo Kim. And it was an idea that was thought up by Marlon Scully out of Texas A&M. And what this is, it's just a modified double slit experiment. And this one may be a little bit hard to follow, but there'll be notes and we can ask questions later. But I'm going to actually go through this pretty quickly, but I'm going to stress to you what the results are and what the confusion and scratching our head about this is. Over on the left where you have the green and gray lines, that's just a light source, so it's a wave coming in. And then at A and B, those are the slits. And then right beyond A and B, that triangle is a photon splitter. It's a crystal that will take a photon and split it into two different photons. And then what the experiment does, and this is a visual simplification of the experiment, but this actually gets to the gist of it. What it does, it actually sends one of those photons up to resolve at destination 1. And on the lower track, it's sending that photon to resolve at D2, D3, or D4. All right? And there's two things I want you to note here at D1. The first thing is, when you look at D1, you cannot tell which of those slits a particle that hit that screen went through. It could have gone through A or B because we're sending upper track photons both to destination 1. And what you see appear there is what you would expect, which is an interference pattern, right? It's a wave pattern. The second thing I want you to note here is that what's happening at D1 is happening 9 nanoseconds before the other destinations get resolved, before the lower track photons get resolved. Okay, so it's before, and it's also a wave pattern there. Then you move forward in time, and you hit this lower track photon, hits this spot, and this is simply a half mirror, which means it has a 50% chance of sending the photon to destination 3, and a 50% chance of letting it go through and resolve at destination 2. And similarly to destination 1, you can look at this diagram and recognize that at destination 3, you know which slit it went through. To go to destination 3, the only way it could have gone was through slit A. And just similarly at destination 4, the only way it could have gone is through slit B. Right? So you know which slit it went through. And what you see there, the pattern, it is a particle pattern, just like you would expect. There's no wave interference because it couldn't have come from B. But when you move forward and you look at the pattern at destination 2, once again, we've erased the which path information. And so we don't know what slit it went through, and we see an interference pattern there, okay? Then we thought, let's fool Mother Nature, right? We should be able to fool Mother Nature because we know back here, we know exactly when these photons split. They split at the exact same time. And we know the speed of light. We know that the upper track photon will hit here, and then 9 nanoseconds, the lower track photon will be resolved. All we have to do is record the times of when these photons hit. And so if we do this here, at D1, we record the time there, and then we move forward and look at D3 and record the time there, then we know that at D3, there is a correlated 9 nanoseconds before the photon hits D3, there is a correlated photon that has hit destination 1. And again, back here, we saw it in its interference pattern, but we know that those particles are ones that went through slit A because they're correlated with destination 3. And so we thought we could fool Mother Nature, and we did that. We then looked at all the particles at destination 1 that were correlated with destination 3. We isolated them out to look at that wave pattern and know these are the ones that went through A. But Mother Nature is not so easily fooled, because what we found out there at destination 1 is those particles, it was showing a particle pattern. It wasn't showing a wave pattern. If you isolate the particles at destination 1 that are correlated with destination 2, it shows a interference pattern at destination 1, right? And now, when you look at it, the reason why it looked like it was an interference pattern back here is because we had interference there at destination 2. Those patterns are showing interference. And if you take a particle pattern and superimpose it over an interference pattern, then it just all looks like an interference pattern, right? It kind of mixes in together. But in reality, what it looks like is happening, again, remember, destination 1 is being resolved 9 nanoseconds before 2 or 3. And yet, it doesn't know later whether it should be a particle or whether it should be a wave at destination 1. It doesn't know that. It's almost as if the particle at destination 1 is looking ahead in time to determine whether or not it should be a particle or a wave. Now, they've ruled that out. It's not looking ahead in time. There's actually some very clever experiments that prove it's not looking ahead in time. But it has everybody scratching their head. And in fact, the most logical, maybe, solution here, explanation, is a term called retrocausality, which means the particles at D3 and D4, or D2 and D3, are actually reaching back in time, or better yet, let's just say they are creating the cause, a later cause, for the effect that happened here at destination 1. So cause and effect is in question here. And there's really there's other explanations for it, but this is sort of the most prominent one. It still has everybody scratching their head. And that gets us back to Planck's statement, where he said that we can't understand nature, especially, and this is his view from the Copenhagen perspective, that observation creates reality. Because what he's saying is that we are trying to study the effects of our observation, and yet the scientific method requires observation. There's no way you can come up with an experiment to test or to try to observe a non-observation, right? And especially now, since there's retrocausality, possibly, even a later observation could have effect on the previous experiment, right? So it's kind of troubling philosophically, and that's why it has Planck being so fatalistic, and why people are saying, we don't know. Most physicists don't actually take a stance on what interpretation is. Most of them say, I'm going to go do my physics, and I don't know what it is, right? Because it hasn't been proven. But that's a troubling concept of the Copenhagen interpretation. Now, if you're like me, when I first heard about Einstein's particle nature of light, I thought it was a bit of a stretch. Because one of the things I knew about light was it had no mass. And if there are any physicists in here, probably laughing at me about this, but I knew light doesn't have mass, and I thought particles have to have mass. So just because light behaves like a particle doesn't mean it really is a particle. It's just some of the interesting characteristics of it, but it's just special, right? It's not like everything else. This is the results of the double slit experiment being done with a green laser. So we know that it is wave, in the Copenhagen interpretation, it is wave, through observation, collapsed to particle. This is a result of a double slit experiment being done with electrons that Hitachi did. You can see an interference pattern there, and electrons have mass, right? So what that means is, in the Copenhagen interpretation, it means that the electron is traveling as a wave of probability to collapse to an electron of certainty once observed, okay? They didn't stop there, they're scaling up. This is 60 carbon atoms arranged in a very specific format called a buckyball. They've done the experiment with buckyballs, and they've seen wave interference. That means that a buckyball travels as a wave of probability to collapse to a buckyball of certainty once observed. And I think the largest they've gone to now is there is an experiment that has almost 1,000 atoms, a molecule made up of 1,000 atoms that have shown interference. And so when we get to this level, there's no reason to believe that it doesn't scale up to everything. That everything exists as a wave of probability only to collapse to that thing of certainty once observed. Right? So kind of troubling philosophically. So troubling that when I say everything, I mean it's quite possibly that it's even the life of Schrodinger's cat. And you may have heard of this experiment. You hear it referred to a lot, where they say the cat is both alive and dead. But let me explain it just a little bit here. basically Schrodinger came up with this thought experiment that said that you have a box, and in the box you have a diabolical device that has a 50% chance of releasing a gas, okay? And then you just put a cat in the box and you seal that box up. When I say you seal it up, that means you seal it up from our classical space. No information inside that box can get released and no information can get put inside of it. Now, we don't really know of a way to actually do this experiment. There's no way for us to have a box that is kind of in this superposition state, but it's a thought experiment and you can do all sorts of things in the thought experiments. And he said basically what we're saying with the Copenhagen interpretation is that when you put it in there and you seal that box up, that the cat exists as a wave of being both alive and dead until we open the box to observe it and collapse one of those certainties. And what's interesting about Schrodinger's cat is he agreed with Einstein. He did not believe in an observer-dependent reality. He came up with this thought experiment to illustrate how absurd the Copenhagen interpretation was. Right? I think he'd probably roll over in his grave now to know that everybody refers to the cat being both alive and dead as if it were a reality, because he came up with this experiment to say, this is absurd, let's move on to something else. Unfortunately for him, I mean, I agree with him. It is absolutely absurd. That doesn't mean it's not real, right? So it's really troubling philosophically. Now, if you're one who has a problem with an observer-dependent reality, again, I have to stress that that's not been proven, it's just not been disproven, right? Can't be proven, like Planck says, we can't prove it, but if you're one that is very uncomfortable with that, and you're in good company, you've got Einstein, you've got Schrodinger, you've got a couple of other luminaries in that space, you've also got this guy. His name is Hugh Everett III. In 1956, Everett was a PhD physics candidate out of Princeton. And he had a big problem with an observer-dependent reality. And he decided he was going to come up with a theory, an interpretation that got rid of the observer-dependent reality. And that's what he wrote his PhD thesis on. He called it the relative state formulation, and it was later dubbed the many worlds interpretation. And basically what he's saying in this many worlds interpretation is he is saying that this image is actually accurate, whereas in the Copenhagen interpretation it's not right because we should see a wave there. He's saying that where those particles can be in this probabilistic state, they actually are there. And there's real there as I am standing here and as you are sitting there. That those particles are in every single one of those places that it could be. Now the first thing you would say to him is, Everett, why are you so crazy? Because when we measure, we only see it in one place. We don't see it in all these places that you're saying it could be in. And he says, well, yes, but that's because you're not measuring in the right universe. Yeah, he's basically saying that every place that that particle can be, a separate universe is spun off that has that particle in that place and has a baffled you in there looking at it saying, Everett, you're crazy. We only see it here. Why don't we see it here? But we're here saying the other thing. So that was born the many worlds concept, that all these universes were spun off from the fact that we have this probabilistic nature. Now, if you think about it, we don't have a way of going to these other universes, right? Nobody's ever thought of it. There's not even a theory as to how to do it. But let's just say you could. If we all were transported to a separate universe that had just the difference of the positioning of one photon, and that was it. It was the only thing that was different in that universe. We would not see any difference between that universe and this universe, except we'd have a twin there that might be a little bit irritated with us, right? But now imagine, just look at the number of photons that are up here, right? And imagine the different combinations that you can come together with those and the different kinds of worlds that can be created. For example, let's say we went to the universe that had all those photons were actually landing all the way to the left, and they weren't illuminating what was on the right. And let's just say that was a wall that had a love note from our love interest on this side. And it was that love note that caused us to fall in love with that person. And yet in this universe, we don't even see it. So you can see how just slight deviations in that can lead to drastically different places. and drastically different experiences. It's an almost infinite number of universes that could be created from this concept. Now, what's interesting to me, Everett, when he came out with this idea in 1956, nobody took him seriously. He was not able to get work in academia. He ended up working for the State Department. And he did die early at a young age, like around 50. But he did see later in his life, around the 70s, physicists started to pick it up, and they started to have conferences on it and wanted to discuss it as a viable alternative to the Copenhagen interpretation. And so it started to gain some more prominence then. But nowadays, it seems to be making a surge. It seems there's a lot of physicists that are willing, and let me just stress that most physicists aren't willing to take a position because neither one of them are proven. Most of them are like, yeah, we don't know, and then they go do their complex mathematics and string theory and all that kind of stuff. But in this case, when the physicists are now willing to take a stance, a lot of them are beginning to more and more, it's actually making a resurgence for this many worlds interpretation. And I think part of that is because there are other elements in physics, other branches of physics that are also positing separate or multiple universes, right? And for example, just very quickly, in cosmology, there's the idea, we have found out that our universe is expanding rapidly and increasingly rapidly. It's not, the idea in the 80s was there was going to be a big crunch. Well, we've determined now that that doesn't seem like it's going to happen because we keep expanding greater and greater. And so the question is the universe going to expand forever? And it's called eternal inflation theory, that we're going to have this eternal inflation of the universe. All the models that are exploring eternal inflation, every single one of them posit a multiverse. They call them bubble universes and multiverse. They posit an infinite number of universes that are created out of this eternal inflation. And then also similarly, in the math of string theory, it also posits multiple universes. So I think it's pretty much accepted. It's for these reasons, all these different branches are starting to posit this. I think it's for that reason that a lot of these scientists are now starting to really look at it much more closely and much more seriously. Now, I said earlier, we can't go to these universes, right? We don't have a way of getting there. But imagine if we did have portals that could get us there. Imagine the very strange and drastically different places that we could go, and the very strange and drastically different lives that we could live, and even meet the very strange and drastically different versions of ourselves. As I was wrapping up the preparation for this talk, I came to a realization that the idea of these portals and the fact that they don't exist for us and we can't reach these places, I realized we actually don't really need to, right? In essence, in many respects, we are already visiting these places. And we're doing that through the narratives that we tell in all of our story mediums, most effectively with the video games that we play. And I can't wait in the future to see what happens as we get more and more fully immersive virtual reality. We will be able to visit these places as if we were able to create portals for that. And maybe that's what this is really all about. That's my presentation. I can take some questions now. Thanks, guys. I don't know, do we have a microphone for this? Okay, thanks. I can't actually see people very well, so. So it's a stand here. I guess we come up and.
Hi. Can you hear me?
No, I can't hear you. Is that mic on?
Hello? Okay,
Yeah, there you go.
maybe it's just me. So just out of curiosity, you posit the idea, or the theory sort of points to a many worlds interpretation. Is there sort of an idea of, like, if you think about it at the small scale, like, oh, the photon went here, but then you start scaling up. But isn't there like a widening, like, you know, if you go one universe over, so what? One photon moved. That means that there's like this band of very, very similar universes that we exist in, but you'd have to diverge very, 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 very far to start to notice like macro changes, basically.
Yeah.
Is there the concept that, like, is there a measurement of how wide sort of the bound is for the...
And again, I have to stress, I'm not a quantum physicist, but in my studies here, I haven't seen any kind of calculations like that. I mean, it's, again, I think from what I can tell, most physicists don't spend a lot of time on either of these interpretations because they can't think of the experiments that would prove or disprove them. And most scientists want to be able to work with what is provable. So right now, they're really more metaphysical, philosophy questions. But I think that would be a great fodder for a story. I mean, my expectation is, I already assume that the PAX crowd is actually a little bit more intelligent and a little bit more creative than your average crowd. And so I'm hoping that we get things like this that will take that kind of creativity and you guys will go create stuff, stories in whatever form you want to create them in. That's what I'm hoping. So I think that would be a great thing to explore in that realm.
Thank you.
Thank you.
Hi. Almost attacked me. In the universe, it didn't attack me. It actually nailed me to the ground. I just wanted to ask, so you seem pretty involved with this stuff, and I myself love playing with the idea of, the world, the simulation kind of thing. And I'm also a programmer. And I know you can't disprove the whole, what'd you call it, observation-dependent reality. But when I see that as a programmer, I'm like, oh, well, the world's a simulation. Why would you do all this work that you don't need to do because no one ever sees it? So it's kind of an interesting concept to play with this. Well, until some entity actually observes it, and when you do that, you kind of, say, raycast backwards, and you create the entire history. You kind of lazy load defer all this work. It's kind of like this interesting, if the world was a simulation, kind of a smart way to do it.
Yeah, there's a lot of people talking about that today too. I mean, the point that the world might be a simulation. It's like, yeah, why would you waste resources on if it's a simulation for us, right? That's where the problem with observation comes in, right? Because we can't know. I mean, like one of my main questions is, can the cat actually collapse its own reality? Is it an observer? Well, we'll never know because later on when we come back to observe, we don't know if it's that later on observation that's causing that collapse. But yeah, that's actually a really good point.
Hello. Okay.
Hello.
Hi. Awesome talk. Thanks for
thank you.
sharing it. Actually, I got a chance to study astronomy and astrophysics in school, so this is all very near and dear to my heart. I was wondering, because this subject matter is super interesting to me, do you have any book recommendations of awesome books to dig in more into?
I
this
do,
stuff?
and I actually have. Here, I'll put it up there. If you go look at my GitHub account, right there, it's the bkirkby.github.io. Go to my projects page. This presentation with references is on there. You can go download it. But the one book that I would recommend, it's not actually a science book. It's more of a science history book. I read it 3 times and I think it's great. It's by Manjit Kumar, and it's called Quantum. And there's a subtitle to that I don't remember, but it's Quantum by Manjit Kumar. I would actually read that. It's actually quite an interesting read.
Awesome. Thanks.
No problem.
How do you feel about the impact of the quantum world on free will? I've heard about a deterministic universe, you're always going to make decisions, but in a non-deterministic universe, it doesn't really matter, it's all random decisions anyway. What do you think?
So the question was about free will, if it's non-deterministic. I have my own opinion. Obviously everybody has their own opinion, but I'll tell you, I like to think that I have free will, right? And I actually, honestly, this does give me a little bit of hope that I do. Right? If things were deterministic, then it won't. But again, I don't know for sure, but I like to think I do. I like to think I make decisions like submitting a panel submission for PAX and actually coming here. I like to think that was my choice to do so, right?
Probably a universe where you didn't, though.
Yeah, there probably is. There's probably multiple universes that I don't. So that's a good question.
Thanks.
At the beginning of your talk, you mentioned how you were interested in quantum computing, and I was just wondering what are your thoughts on this and how quantum computing, that whole thing has taken off.
There's a whole section of the talk that's about that, but we don't have quantum computers that are useful today yet. We have algorithms that when we get a quantum computer, that they will do things. I think the most disruptive thing that will happen there is there's an algorithm called Shor's algorithm that will, when we have a quantum computer to do it, it will make pretty much all encryption obsolete, because it actually is a way to factor primes at very, very fast rates, and that's what all of our security is determined that factoring primes is a very hard problem for computers to solve, and yet it's going to be able to do it like in seconds rather than eons of time. And when that happens, obviously there's going to be some issues. We're not going to be able to order online anymore, or whatever it is that you have that security for. But along with that, remember we talk about observing something changes its nature? Along with them coming up with these algorithms to crack security, there's actually also work on quantum channels. In fact, I think recently China just put up some satellites that are supposed to have quantum channels. And the quantum channel means, this is a little bit technical, but if you look at what we do on our web browsers, we actually do a synchronization of a public-private key. We do a synchronization of public-private key to send a synchronous key across. And then we just use that synchronous key that will encrypt the data and decrypt it. And we do that because it's more efficient. But we don't know for sure whether or not that synchronous key had been compromised. In a quantum channel, you will know at a fundamental physical level whether or not somebody else saw that key. Right? So while there's things to crack the current encryption, there's other encryption that is coming online that is going to make it even more secure than what we have today. So it's an interesting time, although I just saw an article today that said Google is poised to release a useful quantum computer by the end of next year. Yeah, so that's interesting. Thanks.
Hey, thanks for your talk.
Thank you.
In the experiment that you were explaining with the two slits and the 50% mirrors, you said that when the slit B stuff is removed from the D1 location at the top, it shows up as a particle pattern.
Yeah.
I'm confused as to why people are confused about that. Wouldn't it show up as a particle pattern because you removed the wave stuff?
Well, when you say removed, and this is something I wanted to stress inside here, and I don't know if this answers your question, but I'll try to. One of the things that's very interesting about the double slit experiment is it's not like a water wave, okay? Water waves happen because it's water particles all in different places reacting with water particles. These experiments, this wave nature, happens if you send one photon at a time, right? So it's not this photon interacting with this photon in order to create this wave. It is the very nature of light at that stage. If you just shoot one photon out, it is a wave. And so you're not removing the particle in the B track. It can only be, when it gets resolved again to a photon, it can only be one or the other, but it's traveling as a wave through both of them, right? Does that answer your question? Okay. And like I said, you can go look at the GitHub account. You can go look at and it may be just because it's just one of those things that can't be understood really by our intuition. I gotta put that back up there. I think I've got time for one more question, so.
So you talked about the two different interpretations, the quantum state or the many world interpretation. So you gave a couple of examples of games exploring the many world interpretation. Do you know of any games that explore more of the quantum state interpretation, whether in story or mechanics?
I saw one, I downloaded on my phone, I don't remember its name, but there is one that will, it changes its nature, it changes the physical world based on which direction you're looking. Right, and it has quantum in its name. I downloaded it, I played it a little bit, it was on my phone, and I don't really play games on my phone, so I got rid of it, but I would do a search for that, because that's what this game was meant to be. It was supposed to explore that kind of concept. There's not many of them out there. I think maybe, I haven't played Quantum Break, even though it was here in my presentation, but that's more of a time thing, which, what that does, a lot of people are saying that this concept of backwards time travel is a quantum state, so it's actually us going to a different reality in that backwards time. So I think that's all we have the time for, so thanks guys.